welcome to Unit 2.2a. This is part 4. This is the last part in this series. So let's just get started right away with sort of a recap of what we've covered so far in parts 1 through 3. In part 1 and 2, you learn about double replacement reaction. There are two types, acid-base neutralization. And that's where you take an acid and a base, mix them together, and then mix a salt plus a water. There's also the precipitate reactions, and that's where you take two solutions of two salts and you mix them together. They produce two new salts, and at least one of those salts must be an insoluble solid, the precipitate. You also learn how to predict the products of these two types of double replacement reactions. We then went into, in part 3, learning about net ionic equations, which is a simplified version of a molecular equation. And the reason why these are helpful, because they really just show you what is most important and most valuable in these two types of double displacement reactions. This video, we're going to go into stoichiometry, but before we do that, I just want to take a quick note on some phases. Because I want to be clear about certain things. You may need to go back to Unit 2.21, where we talked about ionic compounds, dissolving them in water. And one of the things we talked about with the phases is that if you have an ionic compound and you dissolve it in water, whether it's a base or whether it's a salt, its phase is going to be solid. But any molecular compound, like an amine base or an acid, so molecular covalent ones, the ones with only non-metal atoms, are going to have an aqueous phase. So look, for example, this is KOH. It's because this is an ionic compound, it's a metal and a non-metal, its phase starts off as a solid. Now that we're getting into chemical reactions, because dissolutions are just phase changes, we're getting into chemical reactions where we're producing what we start off with is not what we end up with. What we need to do here is we need to consider what's actually happening. In a neutralization or precipitation reaction, we are not mixing solids, whether they are ionic compounds or not. We're mixing up solutions. So everything is already dissolved in water. So your two reactants are both going to be aqueous no matter what. So this is a quick note that for all of these reactions now, you'll see that all reactants are going to be aqueous because this is what we're doing. So I just want to show you what that looks like. In a precipitate reaction, notice that these are two reactants. In both beakers, you have your two separate reactants. In this one, you have Ki, the one at the top, and the one at the bottom here, you have lead nitrate. And so we're going to write these in aqueous form because they're already dissolved in water. Now that we've made that note on reactants, let's preview what we're going to be learning about here, stoichiometry. So we're going to specifically talk about amount of reactants needed, those sort of problems where you're asked, well, how much of this do you need for that? That goes hand in hand with limiting reagent. We're also going to be talking about amount of products produced, so our theoretical yield, and problems when it's like, well, what's left over after the reactant? Because remember, what should be left after the reactant is not only a product, but also any excess reagent. And that's going to have implications for other things. So let's move on. What's stoichiometry? Stoichiometry is when you're given the amount of something and you're using mole ratios to find the amount of something else. And we talked about this before. The amounts can be moles, it can be mass, it can be volume, concentration. So you can be given the mass of something and ask for the concentration of something else. You can be given the moles of something and ask for the volume or the mass of something else. So that's what a stoichiometry problem sounds like. The mole ratios, which are the keys to stoichiometry, mole ratios are the key, are going to come from your balanced chemical equation and from your chemical formula. So we've seen this before with this example. We have this chemical reaction, potassium hydroxide and lead nitrate. This is a precipitate reaction. The mole ratios will come from the coefficients. So for example, the ratio of KOH to lead nitrate is 2:1, and we get that from the coefficients. You see there's a 2 in front of KOH and a 1 in front of PbNO3, an invisible 1. If you take something like a chemical formula, like KNO3, the mole ratios are going to come from the subscripts. So for example, if you look at the ratio of nitrogen to oxygen in KNO3, it's a 1:3 ratio because the subscript for nitrogen is 1 and for oxygen is 3. You can also do mole ratios when you compare an entire molecule to it's to one of the atoms. So like, for example, if you had 1 mole of KNO3, which is potassium nitrate, you would only have 1 mole of nitrogen. And that's because for 1 mole of this molecule, there's only one nitrogen atom. And again, you get that from the subscript. Okay, let's look at an example problem. So in this example, it asks how many grams of lead nitrate do you need to use up all 5 grams of KOH? And I've given you the balanced chemical equation. If you weren't given the balanced chemical equation, you would have to start here first. You would have to note like what you're given. You're given KOH and PbNO3. So this is a base technically, but here it's going to act just like any other ionic compound in a precipitate reaction. And here are 2 products, and we would use solubility rules to determine that lead hydroxide is insoluble. That's our precipitate. Once you have your balanced chemical equation, let's start listing what we're given. We're given the 5 grams of KOH, and what we're trying to find is the mass of PbNO3. So we definitely are going to be using mole map and stoichiometry. And how do I know that? Remember, I'm going from mass to mass, right? So since we're going from since we're not going from mole to mole, we're going from mass to mass, we're definitely going to use the mole map. And we know we're going to use stoichiometry because we're going from KOH to PbNO3. These are 2 different things. So when you're going from different species, you definitely need to use stoichiometry. Okay, so here we have what we're starting with 5 grams of KOH. We want to get to blank grams of PbNO3. The very first step, as you probably know, is to get the moles of KOH. Then from there, we're going to use stoichiometry, our mole ratios, to get the moles of PbNO3. And then from there, we can get the mass of PbNO3. Our work looks like this: 5 grams of KOH over 1. We put it over 1, so it's a fraction. The second fraction I'm going to multiply comes from the molar mass of KOH. I want my grams to cancel out, so I put the 56.11 grams on the bottom, and 1 mole goes on the top. All right, now I have moles of KOH. I'm here. I want to go to moles of PbNO3. So this is where I use the coefficients in the balanced chemical equation to help me do that conversion. I know that according to this equation, 1 mole of PbNO3 gives you it goes with 2 moles of KOH, so it's a 1 to 2 mole ratio. And since I want to get rid of moles of KOH, I put that at the bottom, and moles of PbNO3 at the top. The last thing I'm multiplying by comes from the molar mass of PbNO3. Again, this comes from the periodic table, this number, and that's going to give me the moles of the grams of PbNO3. So I'm going to cross out things I can cross out, and I see that I have the grams of PbNO3. All right, sorry about that. The species written there was incorrect. So when we do the math here, the grams of PbNO3 will come out to be something like 14.78 or something like that. But we only have 2 sig figs here. We start off with 2 sig figs. So our answer in 2 sig figs will be just 15 grams. Okay. Let's do example 2. We're asked how many liters of a 0.35 molar PbNO3 or lead nitrate do you need to use up all 0.4 liters of a 0.5 molar KOH? So what we're asked in this case, we want to know what's the volume of a 0.35 molar solution of PbNO3. So we have a 0.35 molar solution of PbNO3. And I want to know how much do I need to pour into the container to use up 0.4 liters of a 0.5 molar KOH solution. All right, so in this case, I'm going to from molarity and volume of one thing, so molarity and volume of the KOH, and I'm using that to find the volume given the molarity of PbNO3. Since I'm going from molarity and volume to molarity and volume, this is where we use the shortcut. All right, so we're just going to use the M1V1 equals M2V2 shortcut. And since the species we're going from is KOH to PbNO3, which are not the same species, we do need the N's that are shown there in purple, which will take care of our mole ratio. So that part takes care of our mole ratios. So let's look at how we do this. It's super important whenever you do this, you need to set up and determine what substance 1 and what substance 2. So for substance 1, I'm going to start with the KOH. According to this, it has 0.5 molar, so its M1 is 0.5 molar. And the volume of it is 0.4, so V1 is 0.40 liters. So remember, substance 1 would correspond to anything labeled 1, so M1, V1. And now N1, according to the balanced chemical equation, the coefficient is 2, so that's where that 2 is. So here it's going to be 2 moles. We do the same thing for substance 2. So substance 2 is my PbNO3. My M2, they tell me, is 0.35 molar. My V2 is what I'm looking for. I'm looking for the volume. And N2 is going to be the coefficient in front of PbNO3, which is 1 mole. Okay, so I set it up, plug everything in, do the math, and I get the volume is 0.3 molar solution. And the reason why I'm using one sig figs is because I have one sig fig here. Okay, now you have some CFUs, CFU 3 and A and B. You're going to take a moment to read through the CFUs. You're going to try these on your own, and then the answer will be revealed when you are ready. Before we go on with CFU 3A, I figured I'd give you a hint. Make sure this is a case where you're using a theoretical yield. You ask how many grams of PbOH2, which is your product, can be made by mixing 400 milliliters of a 1.8 molar KOH solution and 350 milliliters of 2.5 PbNO3 solution. So basically, you're given the values for both reactants. You don't know which one is limiting. You're just given their amounts, and you want to figure out how much product you can make. So now that you've seen that, maybe you want to give it another go, knowing that this is a limiting reagent theoretical yield. Remember, there are two methods you can use, method A, method B. It's your choice. All right, here's what the work would look for. For method A, we would ask the question, how many milliliters of KOH do I need to react with 350 milliliters of 2.5 molar PbNO3? So basically, I'm going to figure out, I'm going to choose one reactant to start off with, and I'm going to figure out how much of the other reactant do I need. So I'm looking at PbNO3, and I'm figuring out how much KOH do I need for the amount of that I have. We're still going to use a shortcut since the information we're given is molarity and volume. So this is what that will look like. So when I do my math, I determine the volume of KOH I need is 972 milliliters. And I go back up here and I see that I have for only 400 milliliters. So clearly I'm going to run out because I need more than I have. Or I have less than I need. And so KOH is my limiting. The second step is to utilize my limiting to calculate the theoretical yield. So now I'm asking myself, well, how many grams of PbOH2 can I make from 400 milliliters of a 0.18 molar KOH solution? So remember, this is my limiting reactant. I'm using that to figure out how much product I can make. Since they want it in grams, I can't use a shortcut because I'm going from molarity information to grams. So I'm going to use sort of the mapping here. This is what the work would look like. From molarity and volume of KOH to moles of KOH, from moles of KOH to moles of PbOH2, and from moles of PbOH2 to mass of PbOH2. And that will give me 87 grams. For method B, that's where you determine the amount of product you can make from each reactant separately. So I'm going to figure out for the amount of KOH I have, how much of this I can make. For the amount of lead nitrate I have, how much of this I can make. And then the one that gives you the smallest number is your theoretical yield. So I'll start off with how many grams of PbOH can I make from 400 milliliters of 1.8 molar KOH. And so my mapping looks like this. And that gives me 87 grams. I do the same thing for, so at this moment, I don't know what's my theoretical yield yet because I need to figure out which one will give me the smallest number, and that'll be my theoretical. So I'm going to repeat the same thing, figure out how much of the PbOH2 product I can make from my other reactant, which is lead nitrate, and this is what that work looks like. And this gives me 210 grams. So because the previous one will give me a smaller number, 87 grams, this would be my theoretical yield. Okay, so you can use any method you want. Let's move on to CFU3B. Here's the answer for that. After solution mix, what is the expected concentration of nitrate ions? So we kind of figure out, first of all, we know KOH is our limiting reactant. That means all of it's going to be used up. But not lead nitrate, that's our excess. That means that some of the lead nitrate is still going to remain. So so some of the nitrate is still going to be in the lead or come from the lead nitrate reactant. We also have some in the potassium nitrate. And so this is sort of just a particle diagram of what that sort of looks like. Let's say, for example, we start off with 4 moles of each reagent.